All right, let me do this. It's all about me. Bam. All right. All right, guys. So if there's no questions at all with all this freaky ass homework I've given you, there's no questions. I want to make sure about that. All right. Okay. And if you haven't done the quiz yet, it's still up there to be done. Please don't try to do it during class. That's a bad idea. I'm gonna see that you're doing it, and I'm gonna kick you out. Let's see. Let's see where to go. Here we go. Oh wow, I am like really tired today. I don't know how you guys are feeling. So just remind you guys, it's due tomorrow at 8 a.m. the quiz, so you have some time to get it started and to turn it in. If there's no questions from any homework, I all right. I don't know how to feel about that. We can just get right back in to where we left off. We can finish up chapter 8. Okay. So what do we have left to do? We need to go back and take a look at tangent and cotangent. We need to create those, what do you call it? Graphs. Today's going to be neat. I'm really tired. We need to figure out what they look like, the graphs, and then we can talk about their shifts and stuff. Let's see. Yeah, let's do this. I'm gonna be a little lazy. Why not? No. All right, let me see if I can make this go over there. Okay. Come here, you. There you are. There we go. All right, you guys can see my little Zoom whiteboard, right? Anybody?
Yes.
Okay, cool. Thank you. All right, so we've talked about sine, we've talked about cosine. Let's just let's do this. All right, let's do that. Let's do this. Let's do something a little better than this whiteboard thing. Let's do that. I'll do the whiteboard in a minute to talk about tangent and cotangent. Let's go back to that handout, that worksheet that's up on Canvas. Let me show you where that is, just to remind you. So it's down in unit. Oh God, help me. Unit 8. Was it this guy? It's got to be this guy. Yeah, so we did this one yesterday, the cosine. Let's see. So I want to do cosecant. So it's up on Canvas. It's in the. Let me show you again where it is. We looked at this yesterday. You go to Unit 8. You're not going to see this other stuff. Sorry, I'm not a student at the moment. It's going to be this trig graph practice. You can only see these two, right? In Canvas. Go to trig graph practice. It just rolls off the tongue. We did this side yesterday. So today we're going to do this side. All right. So I'm going to stop sharing. I'm going to share this in a better way for me. All right. Oh, so much technology. Help me. Okay, I think this is it. Ooh, please let me know. Yes. Okay. All right, let me share this. Oh, I have no idea what this whole experience is like for you guys. Just waiting for the teacher to get something to open. All right. So let's look at this weird thing. Cosecant. What is that based on? Hello? Cosecant. What is that defined?
Sine.
Yeah. Is that cool? Based on sine. So in general, cosecant x is 1 over sine x. So what I'm going to do, I need you to understand the idea of amplitude doesn't make any sense for cosecant itself because it's going to go to infinity. Side note. Somebody help me out here. What is the cosecant of 60 degrees? Can somebody, how would I figure that out? Did I ask you to memorize anything about cosecant? No. Could you if you wanted to? Sure. I would highly recommend you don't. But what'd we just say? What's the cosecant of 60 degrees equal to that we do have something memorized for? Cosecant of 60 would be 1 divided by what?
Sine.
Holy crap. Yes, sine of 60 degrees, right? Because cosecant is 1 over sine. Secant is 1 over cosine. Okay, I like it. And who knows what sine of 60 is?
Square root of 3 over 2.
Kick ass. So this will be 2 over rad 3. So it'll be 2 rad 3 over 3. Okay, so that's not my point. Here's my point. What then is cosecant? You can do it, Jeff. What is cosecant of 0 degrees? So really, what is sine of 0 degrees? What's sine of 0?
2 pi?
No. So you just gave me a radian alternate way to refer to 0 degrees. I want to know what the sine of 0 degrees is.
Just 1.
Okay, guys. You got me very concerned. All right.
0?
Yes. But I'm still concerned. Rio can try to save your ass, but he didn't make it in time. So, if you do not at this point have the first quadrant memorized for sine and cosine, you are way behind. Way behind. Ooh, Jeff's getting all angry now. All right. If you're having trouble memorizing it, you could always ask for assistance. I've tried to give you a few different ways to memorize stuff, right? I've given you the way that I look at things. You have to pick something. You have to have done it already. It should have already happened, right? So if I ask you, what's the sine of 30 degrees? To answer that question should take at most 10 seconds, at the very most, right? So what is sine of 30 degrees, for example?
1/2.
1/2. I like it. And the way that I think of it, this doesn't have to be the way that you think of it. Sine likes y. 30 is far away from the y-axis. Sine is going to be the smaller option. Because it could be 1/2 or rad 3 over 2, correct? Are we at the point where you understand what I mean when I say that? Because where is it rad 2 over 2? Where's the sine rad 2 over 2? What angle?
$45 degrees.
45 degrees. I like it. Or pi over 4, right? You can do that too. I like it. All right. So 45 degrees or pi over 4 in radians. Okay, I like it. I like it. Okay. So you have to. The quickest way, if any of you guys are taking calculus, and even if you're not taking calculus, you're in pre-calculus. You got to know the shit for this class. But if you're taking calculus, if on the first day of calculus, I give my students a little pre-warm-up thing, and they don't know what sine of 30 degrees is, I get really, really concerned. It's bad. It's a bad thing. Okay, so you have to have a way to know what these are. So coming back, cosecant of 0 degrees equals 1 over sine of 0 degrees. At 0 degrees, it's all x. no y. So sine hates it there. So this would go to 1 over 0, which is undefined. Okay. Which is actually what? We know better now. What is that really? I mean, what does that mean? As theta goes closer to 0 degrees, what does the cosecant do? Yeah, there, Jeff.
Smaller.
No, definitely not. Sine does. Sine goes to 0. What does cosecant do? All right.
Bigger.
Sorry?
Bigger.
Yeah, because what does this really mean? I mean, somebody help me out. Okay. In your calculator, can somebody tell me what is the sine of 0.1 degrees? Can you do that in your calculator for me real quick? What's the sine of 0.1 degrees? Does it really say 0? Wait a minute. I guess it could. It's not what I expected. Hold on.
0.00174.
Yeah, so it's 0.00. I like it. Thank you. 001745. Blah 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 blah. Now, what's 1 divided by that? Which would be the cosecant. So if you do 1 divided by what you just did, what do you get?
572.
Yeah, 572. Who cares? It's huge. It's crazy big. So what's going to happen when I get even closer to 0? This is going to get even smaller because sine hates it at 0. It's going to go to 0. So it's going to get smaller, which means this is going to get bigger. So we know that undefined on a graph, most often that means there's going to be a what there. If the function is undefined at a point, most often that means what's going to be there. We talked about it already. You actually asymptote. Kick ass. So normally that is what undefined will mean is going to happen. Not all the time. It could be a open circle or something there, but something weird's going to happen there. Okay, so coming back, let's see. I got to remember what I was doing before I did all that. Let's see. Oh, here it is. All right. So this is undefined. All right, so I know that, no, I forgot what my bigger point was. I know this is going to have issues. It's going to have places where it goes to infinity. It's going to have asymptotes. It's going to have asymptotes everywhere that sine equals what? Cosecant has asymptotes wherever the sine is what? You could do it. We just identified.
0.
Yes, wherever the sine is 0, cosecant is going to have an asymptote because this kind of thing is going to happen. Are you guys with me at all? Even a little bit? No. Don't say anything if you're 100% with me. All right, good. Now, my whole point with this, now I'm remembering, the amplitude doesn't make any sense for cosecant. Can somebody tell me why, based on what we just talked about? Why would the idea of amplitude make no sense for a function like cosecant? Is cosecant, would you call cosecant bounded? Would you call it bounded? Would you call it contained?
It's like big, too big.
It goes to infinity, so it's not contained. Does that make sense? Would you call sine contained? Here's sine, right? Would you call sine contained? Is it contained? Do you guys understand what I mean by contained? Would you say that sine is contained? Does
Yeah.
it have a maximum and a minimum? Yes. Cosecant, does it have a maximum?
No.
Because it goes to infinity at some places, and it goes to negative infinity at other places. All right, so why do I have amplitude down here then? Because the way you graph cosecant is to first graph sine, and then you can graph on top of that. Are these going to go away? Oh my gosh, help me. All right, everybody just hang out. I
I
can't.
have a quick question,
Yes, please. What's up?
but sine also can have what do you call it? Like no amplitude when it has like a x times sine x.
Oh, yeah, sure. The minute you start, so that's not a sine function anymore, is it?
Oh, okay.
Yeah. That's the product of two functions, so it can do whatever the hell it wants to.
Thank you.
Yeah. So you get really cool shit. Like, I might show you in a minute when you marry exponential function with the sine function, you get some cool shit. So maybe we'll graph that in a minute, or you can graph it on your own, but then I'll graph it in a minute too.
So in my case, what I said, x times sine x,
Yes.
is x considered to be amplitude?
In a way, yes. So it's a functional amplitude. It's an amplitude that is not constant ever.
Okay. Yeah.
It's constantly changing. So it is the amplitude, but it's not really the amplitude. The same way you can't say the slope of a parabola, can you? Because it's always changing.
Yeah.
Okay. I like it. All right. Stay with me. Now, a lot of cool shit just happened. All right. So let's do this step by step. The first couple of things are going to be very familiar. In fact, everything's has to be familiar because we're going to treat it as if it's a sine. We're going to pretend like it's sine for a minute. Right? So first thing I do is to factor inside. Why do I factor inside? I'm not going to actually write sine. We're just going to go with me. Why do I factor inside? What does that do for me?
E times plus 1.
Sure. But what does it do for me?
You can determine phase shift.
Yeah. I might have helped out. All right. Let me stop for a minute. Because does everybody agree with me? What would the phase shift be? What goes here? It shifts by how much to the which way? Somebody else tell me.
What is to the left one?
Shifts by 1 to the left.
Yeah.
Kick ass. And I didn't know that until I did this factoring first, right? I like it. Now somebody else tell me what K is.
Pi over 4.
Pi over 4. Kick ass. All right. I'm working through all my people that normally talk to me. All right. Now somebody else tell me what the amplitude is if I'm pretending like it's sine for a minute. What would the amplitude be for the sine function? This is an easy question. So your time to shine now, somebody. Anybody?
2.
2.
Well, I shouldn't have said anybody. I still meant whoever I haven't heard from now. All right. And then the period, you do what the period normally is, divided by K. All right. Everybody freaks out about this. That is 8. So easy. Pi's die. 2 divided by 1/4 becomes 2 times 4. So that's 8. So if I want to look at the whole thing again, 2 pi divided by pi over 4 is 2 pi times 4 over pi. Everybody with me? Because you multiply by the reciprocal when you divide by a fraction. The pi's die. That's sad. Never like to see pi die. 2 times 4 is 8. So that's the period. Okay, I like it. Maybe. And again, this is not a bad thing to do. I really kind of want you guys to do this, but the more you get into this, the more you'll realize you don't really have to do this, but let's just do it. So can you guys just take a minute? Don't say anything. Just go ahead and solve those two. Solve those. Oh, wait. Solve those two little equations. Remember what this means. Doesn't sine start at 0 when the inside is 0? So the inside is 0 and the inside is 2 pi. If I solve for x, it'll tell me where my new function starts and where it ends. This is a beautiful little thing you can do for any periodic function, really. So I have no idea if anybody's doing the work, but just take a minute, solve those two. So watch this. I would first divide by pi over 4. That becomes x plus 1 equals 0. So I get -1. So over here I'm going to do the same thing. Let me divide by pi over 4. Didn't we just do this here? Is this the only way to do this problem? No. Is this the easiest way to do it? Oh shit, yes. Anybody out there with me? You guys with me at all?
Yes.
There's a couple people. Thank you so much. If you're not with me, if I lose you at any moment, I can guarantee you, you are not alone. No reason, there's zero reason to not speak up and say, what the shit just happened? Maybe don't say that. You don't have to be that like that with me, but okay. Why does all this make sense? Aren't I supposed to shift by 1 to the left? Yes?
Yes.
Don't I normally start at 0 when I'm trying to graph? And we know it goes forever, but just to start it, I start at 0. So of course it makes sense I'm going to start at -1. And then the period is 8. So shouldn't I go to 7 then? Doesn't it make sense I'm going to start at -1 and go to 7? That also shows you why this is unnecessary. But it is kind of nice to see, oh yeah, it's doing what it's supposed to do. Okay. Maybe? Maybe? No? Screw you, Jeff. Okay, so let's see if we can put it all together. So I want to start at -1, and I want to go to 7. Oh, crappity, do that. 1, 2, 3, 4, 5, 6, 7. All right, I guess we'll do a normal. But, all right, I really, really don't know. I just don't. But I'm going to try. I don't know if you guys are with me about what are can somebody tell me what the main, so I'll start 0, and then there's 1, 2, 3, 4. And I keep coming back to this. What are those 4 key anchor points? Can somebody tell me what this one is?
Pi over 4, 2.
Half a pi.
So this is pi over 2, which is 90 degrees. It kind of makes sense. If you look at the unit circle, what are the 4 most important things? 0, there's 5 actually. 0, pi over 2. What's this?
Pi.
Pi. What's this?
3
3
3 over 4 pi.
3 pi over 2, and that takes me back to
pi.
do. Do, 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 do. A deer. No, it's 2 pi. You're right. Sorry. Those are the anchor points, because then sine normally does this business, right? Starts at 0, goes to highest, goes back to 0, goes to lowest. Where am I at? Why is that there? Oh yeah, okay. I'm with you. There we go. Wow, that's what sine normally does, and then it goes forever in both directions. Weehaw. Right? So that, if I ask you, draw like a standard parabola that hasn't been shifted, you should be able to very quickly do this, and then you got it. You guys kind of with me? And isn't this the same anchor points I use if I'm going to shift the parabola? I'm going to use those anchor points. So we are just incorporating, for example, the sine function as just another function that we know the shape of, and we know the anchor points. It's the same thing. So sine function's kind of like, ooh, it's amazing. Ooh, it's this whole thing, but it's just another frickin' function. It's just another function. So it's got its anchor points, it's got its shape, like any other function, right? All right, so can somebody tell me how big the steps are gonna be? So normally the steps are pi over 2. Everybody with me? Normally the steps are pi over 2. Because all right, I have no way of gauging if you're with me, so that kind of drives me a little crazy. So I'm sorry if you are, because I normally go from 0 to 2 pi in 4 steps. So if I do 2 pi divided by 4, this tells me how big each step is gonna be. We did this last time. We did this the time before that. So what's my whole period now? What's my period?
8.
8, right? So 8 divided by 4, what's my step size going to be?
2.
2. So I know I have all of these down here because it was an easy scale. Is everybody with me? I want to fill all these numbers in, but what are the major numbers? -1, 1, 3, 5, 7. Let me see if I can push this a little further. All right, whoops. This, get out of there. Can you guys see my graph again?
Yes.
All right. So this is related to 0. This is related to pi over 2. This is related to pi. This is related to 3 pi over 2. This is related to 2 pi. So all I'm doing is taking this shape and where it normally does things, and I'm stretching it out and I'm moving it around. So normally I start at 0 at 0. So now I'm going to start 0 at this point, and then I take one step. So now I'm here. And what's the next place I'm at? So actually be careful. What's the amplitude of this bad boy?
2.
2. So now I'm going to be, the next step I'm going to be the highest point. And then the next step is 1, 2. I'm going to be at 0. I'm going to be back to the midline. And then the next step, 1, 2, I'm going to be at the lowest point. And then the next step, 1, 2, I'm going to be back to 0. Now this I'm going to do as a dotted line because this is not the answer yet. Can somebody tell me why this is not the answer yet? I should do more. Ah, screw it. This will be fine.
Because that's the graph for sine.
Good. And we're trying to do the graph for, yeah, we're done pretending now. We're trying to do the graph for cosecant, right? All right, this is going to be my most colorful graph ever. What graph? You feeling pastelish? No. What am I feeling? Gold? Sure, why not? Does that show up? It looks more like mustard. What about teal? You guys like teal? Teal works, okay. So, I see with what we've drawn here, 3 locations of an asymptote for my cosecant. Can somebody tell me 1 location of an asymptote? Since the cosecant is 1 over sine, there will be an asymptote wherever sine is what?
0.
0. So somebody tell me 1 location where sine is 0 on this graph.
-1.
-1.
I love it. Now somebody else give me another location of an asymptote.
7.
7, look at that. We go way over here. I love it. And what's the last location in terms of what I've got drawn here? My asymptotes are all crooked. Too bad. 3. And then look, now watch. This is how cosecant and secant work. If you can graph sine and cosine, like we just did, to do secant and cosecant, all you have to do is this. That's it. And of course that continues. So it really looks like wah, wah, forever in both directions. I'm not going to graph all of them. That would take forever. Literally would take forever.
So does it have two parabolas in one period?
Oh, yeah. Good way to look at it. So one cycle has kind of like two parabolas. I call these two cups because they're not really parabolas, but they do kind of look like cup up and cup down. Is that cool?
Yeah.
It's got a cup up and a cup down, and that makes a whole cycle, which kind of makes sense because what makes a cycle of a sine function? A hill and a valley, and that corresponds to a cup up and a cup down. Yeah. So to make a complete cycle would be one cup up and one cup down. Kick ass, kick ass. Now, again, I know it's relatively new, this whole idea, but the minute you get the idea of a sine function down, you can graph a sine function, that immediately means you have to be able to graph a cosecant function, because a cosecant is just one more step. All right, so if you're like, I can't even graph a sine function yet, Jeff, well, then that's your next immediate thing you want to practice. Graphing sine and cosine. I like it. Okay, maybe. All right, so let's do this. Any questions on that? That's a lot of colorful jumble of spaghetti going on there. I love it.
So cosecant kind of have a horizontal asymptotes too?
Yeah, what do you mean, horizontal? No. Not really. Why is there's no horizontal asymptotes? Because there's nowhere that it's approaching something horizontally. It's got kind of like an excluded middle, but it doesn't have an asymptote. It's not approaching something horizontally. It's only approaching something vertically.
Yeah.
All right, now I gotta apologize. Hold on. I'm really bad at keeping up with chat when I'm sharing my screen, and I'm sorry. Some people were answering me. Somebody had a question. Why did you cross out? Oh, okay. Is that question still one that you have, person out there who has private chatted me? How did I graph this? Didn't I have to what did I first graph? I pretended as if the question was what? Yeah, I base it off a sine. And then I remember, oh shit, it's not sine, it's cosecant. Okay, so let me make this dotted so then I can draw the real answer on top and bottom of it. I got you. So if it said secant, I would pretend like it said cosine, do all the work, and then the very last thing I do is put my little cup up and cup down. So that's really nice if you let it be. Why does this make sense, by the way? If I've already forgotten what it was we did. Oh, if cosecant is 1 over sine, then wherever sine is 1, so if sine of some angle is 1, what would cosecant of that angle be? Cosecant is 1 divided by sine. So if sine of some angle is 1, what is cosecant of that angle? What's cosecant defined to be again? 1 over sine, correct? All right, so what is cosecant going to be? If sine A is 1, what's cosecant A? 1. So that's why they agree. That's the one place where they agree with each other, because it works for -1 also. Do you guys see what I'm saying? So it's really neat. It kind of should make sense. The biggest sine can get is 1. The smallest, the upper part of secant can get is 1. The smallest sine can get is -1. The biggest, the lower part of secant can get, cosecant is -1. Because they're not inverses, they're reciprocals. I gotta be careful they're reciprocals of each other. So that kind of hopefully makes sense. Okay, that's enough of that. That's enough. Okay, so let's transition to this last section. Let me bring back my whiteboard. Okay. So this last section, oh, it's still up here. That's so cool. This last section is all about truly inverse trig. Yeah, functions. Holy crap. I could go back in time. I don't know. Do something to get my writing better. Oh well. So, what is the problem? Can somebody tell me the most fundamental problem? Let's start with sine. We almost always start with sine because it's the most fundamental kind of trig function. What is the problem with figuring out inverse of sine? Can somebody identify what does it not meet? What requirement does it not meet? What's got to be true for something to be invertible?
1-to-1 function.
Good. What makes something a one-to-one function? Somebody else. Does anyone remember? What makes something a function? What test do you apply to see if it's a function?
Horizontal line test and vertical
Right.
line.
Yeah, vertical line test for a function, horizontal line test for one-to-one. Does this pass the horizontal line test?
No.
No.
Hell no, right? In fact, how many times would a horizontal line drawn like right here, how many times would it cross through the sine function?
Infinite.
Infinite number of times. I love it because it keeps doing this. It keeps doing this forever in both directions.
So
Yeah.
for it to be 1-to-1, you take the x and y and swap them, right?
No, careful. You're thinking about how to find the inverse. What did we have to do with a parabola? So if I have a parabola, what did we have to do with the parabola to make it invertible? To make
Get rid
it
of one
one-to-one?
side.
Say again, sorry?
Get rid of one side.
Yeah, get rid of one side, right? If I got rid of one side of a parabola like I just did right here, is that invertible now? Is that one-to-one? Does it pass a horizontal line test? Yes. So I should have drawn this bigger. Let me focus on the main parts here. All right, so here's the sine function, right? Jeff, this is really gross, but that's just too bad. It's just the way things are. So here's the sine function going through, wee-haw, and it goes down, woohoo. If I would have been smart, let me see, can I go back in time? I can, because I'm neat. All right, let me be smart about this. So here's the sine function, it's going through. Yeah, it's going through. Woohoo. All right. So, and kind of, does it make sense the part that I've drawn? Because I could actually do what I'm about to do way the hell up here if I wanted to, but doesn't it make sense to do it as close to zero as we can to cut something off to restrict the domain? I could do it anywhere I want to be honest. But this is going to be the definition of the inverse sine. It's going to be close to zero as it can be. Where do I want to start chopping things off? Sort of like over here, I started chopping off at 0, didn't I? It could have been either side, but I decided to chop this side off, or you guys did, or maybe I did. I can. So where do I want to start chopping here?
Pi/2.
Yeah, because that's where things start to go wrong, right? Look in the middle here. Isn't everything beautiful? Isn't everything beautiful until you get, damn. That's why it doesn't pass the horizontal line test. This part, get out of here. What about back here? Obviously, I want to do starting at, just say it.
-pi/2.
Thank you. All right. So what does this mean? What this means, all right, this is going to get, now this is where things get interesting. Let me see here. Can we graph the inverse of this? We can. Somebody help me out. What is pi divided by 2? Isn't that roughly 1.57? Right, 3.14 divided by 2. It's 1.57, right? Okay. So somebody help me out. What point is this right here? What point is this? Didn't want to do that. Darn it, didn't want to do that. All right, let me do it again. What point is this? Just tell me, what point is that? What point is
One.
this? Say again, sorry. Go ahead.
Pi over 2, 1.
Good, so let's just say 1.571, cool? Just approximately. So this point is gonna be negative 1.571, right? And of course, this point is 0, 0. So if I wanted to graph the inverse sine function, sort of like we graphed the natural log before we even knew it was a natural or a logarithm, sorry, let's just say a logarithm. Remember that? Do you remember that? We graphed what it looked like before we even gave the poor dude a name. You guys remember that? You're like, we did that? I don't know, Jeff. Doesn't sound like something I would do. All right. Let me see. What's a better color here? I have no idea. Doesn't matter, Jeff. Okay. So now watch. I'm going to graph the inverse. How do I do that? You guys remember how to graph the inverse? How do you always handle an inverse? I do what?
Switch.
Switch the x and y. So I'm going to graph the point 1, negative 1.57. Right? So 1 is about right here. This is 1.57, right? So 1 is about right here, let's say. I don't know what makes sense. Here, okay. So this is about 1. So I want to graph the point 1, negative 1.57. So that's about right there, maybe. And then I want to graph the point 1. Why am I saying 1 back here? That's the problem, Jeff. Let's try this again. That's my fault, everybody. Hold on. I put a positive 1 down there. Let me correct this past mistake. All right, Jeff. There you go, buddy. All right. Maybe I should use a different color too. All right. Hold on, everybody. What color is this? I have no freaking idea. All right. So I want to graph the point. Let's start with this one. I want to graph the point. Turn this around, right? I want to turn this around. 1, 1.57. This can be about right there, maybe. And I want to graph the point negative 1, negative 1.57. So it's going to be down there, maybe. And it's going to also go through 0, right? So it's going to look something like this. Well, this is going to be freaky. And see how it goes? It's reflecting around the y equals x line. Right, this is not the best picture in all of the universe, right? So that's what it looks like. And we actually don't give it well, there is a special name we give it. So this function is called, we either use this symbol, inverse sine, or something that's not used as much. And I will tell you this, I personally don't use this at all, really. But you see sometimes it's also referred to as arc sine. Arc sine means the same thing as inverse sine. Are you guys? We've seen weirder shit for names of functions, so you're okay with that, right? We call a function a frickin' log. Are you kidding me? So arc sine, it sounds like something to do with Tony Stark. I don't know. The arc reactor? No? You're over MCU? I don't blame you. Okay.
So does it have a limited range on the domain?
Good. So let's talk about perfect. Look, it's like I plant you out there. So for the function sine x, what's the domain? What's the range? If I'm gonna the truncated, how do I want to say this? You can do it, Jeff. What is it you call it? Restricted. There it is. Gosh, I'm tired. Restricted domain. What's the restricted domain? What did we do with this blue line? What did we restrict our domain to make this possible?
Have a bracket,
Yeah.
negative pi over 2.
Yeah, negative pi over 2 to pi over 2. I like it. And what was the range, of course? What's the range of sine? Somebody else.
Negative 1.57.
No, come on, no. Don't look at the red thing. That's the inverse sign. I'm talking about sine right now.
Oh, -1 to 1.
Well, they go 1 to 1. I love it. So what's true for inverse sine then? What will its domain be? You could do it. What does inverse functions do to functions? They switch the x and y, correct?
-1 to 1.
Good. -1 to 1 for the domain.
Then negative pi over 2, pi over 2.
I love it. Kick ass. I like it. Now, what the hell does any of this shit mean? What this means? Okay, let's stop sharing. Oh man, there's chats. I told you. I'm sorry. I can't keep up with those. All right, I'm gonna stop sharing. You guys ready? I want to do two things. I want to remind you about something. I can't remember now. Let's go take a look. Let's see. I want to show you something. I'm gonna stop sharing. Here it goes. It's all gone. Okay. Now, I kind of want to see what I put up here for you guys in Canvas. I can't remember if this is on here or not. There's a trig sheet, a basic trig sheet. Do you guys remember that I put up here? Trig basics. And it's got stuff about the graphs. Yeah, I don't think it's got anything about the inverse. No, okay. I didn't put anything up here about the inverse. There's a reciprocal. Look, here's the cosecant. Here's the secant. Right? In fact, you can even imagine to yourself, like here, you can even imagine to yourself this kind of thing going on, right? Do you see what I'm talking about? Do you see what I'm talking about? Do you see what I'm talking about? No? Yes? Maybe? No? No idea what you're doing, Jeff? You're weird? All right, shit. So this is the whole thing we just did, where sitting on top of a cosine would be the secant. The cup up and the cup down. Okay, I'm trying. All right, so let's do some stuff up here on the board. So we can finally do this. In fact, I really didn't lay the groundwork for this, and that's just my fault. But we can finally do something like this. Like what, Jeff? I don't know. Oh yeah. What? Can somebody remind? Do you guys remember? There's a 3, 4 what triangle?
5.
3, 4, 5. I love it. How do I find this angle? We haven't been able to do that until now. What can somebody give me a trig function that you want to use that relates this angle with the sides? Somebody else. You could be anything. Any trig function will work here. Maybe one of the three main ones to make it easier. Go ahead. Sorry, Maida.
Tangent?
Okay, tangent. Tangent of theta. Well, all right. I'm just kind of being silly. We've only talked about inverse sine at this point. So let's do sine. That was my mistake again. I'm tired. We've only talked about inverse sine. So let's do sine. What would sine of theta be?
3 over 5.
3 over 5. I love it. So now watch. And real quick, a little side note. Stay with me. Side note. How would you solve, just go with me. This is going to be a little weird. How would you solve cube root of x equals 2? What would you do to both sides to solve that?
Cube.
You would cube both sides. You would apply the inverse function to both sides, correct? Is everybody with me? You would apply the inverse function to both sides. How would you solve this equation? Somebody else. Bowen, you're getting a little ahead of me. We're not quite to that point yet. Law of cosines deals with non-right triangles. Somebody help me out. How would you solve this equation? Yes, you would apply the natural log to both sides. Why? Because what does natural log do to e?
Cancels out.
Kills it the same way that killed that. Why does that kill this? Because they are what kind of functions? Why do they kill each other?
Inverse.
Inverse function, I like it. Yes. This is how we solve equations. We apply inverse functions. We just don't call them that at the beginning. Right? What's the inverse of addition? Subtraction. So how do you solve an equation with x plus 2 equals 7? You apply the inverse function, which is a really technical way to say subtract. All right? All right. So what would I do to both sides of this? Let me write it again. I need some more room. What would I do to both sides of this to solve for theta?
Cosecant.
No. I don't apply the reciprocal function. That makes no sense. The only way to kill a function is with its with fire. No, it's with its inverse. Yeah. Fire doesn't phase these. You can't kill them with fire. It's too bad. So I have to apply the inverse sign. So what do these two do to each other?
Cancel.
Cancel. The same way these cancel. The same way these cancel. These cancel. So you have the theta equals this. And do you guys see this button in your calculator right above the sine button? All right. So let's figure out what the shit that angle is. Let's figure it out. I think it's 42 point something. If I could be
I
totally wrong.
got 36.9.
I knew it. I'm totally wrong. What am I thinking about? There's something about that angle that's special. It's not that, I guess. It's not that, Jeff. It's too bad for you. You got to be careful about what mode you're in, right? Okay. So yeah, I agree with you. You get 36.9 roughly. Yeah, I like it. Depending on how much I want you to round. 36.9 degrees. How many radians? So if you put your calculator in radians and do it, it'll tell you how many radians. So it actually comes out to 0.644 radians. Okay. So that's a very useful ability to have, to find the angle given the sides of a triangle. Okay, I like it. Now, oh, sorry, go ahead.
So what does 3/5 represent in parentheses?
That's just the ratio,
Ratio.
right? I mean, right here, this was where we started, correct?
Yeah.
Now, real quick, we haven't developed inverse cosine yet, but what would happen? What's the cosine of this angle? What's the cosine of this angle?
Oh, I think I got it.
I'm going to still do this. What's the cosine of this angle? You can do it. Sine is 3/5. Cosine is 4/5. So what would I do in the calculator? Wouldn't I do inverse cosine? And you already know what you're going to get. You should know what you're going to get, but go ahead and do it. If you do that in the calculator, you better freaking get this, because that's what the angle is. It doesn't matter which trig function you identify it with. You guys okay out there? All right, now I'm going to show you a shortcoming of the inverse sine and inverse sine, because we haven't really talked about cosine yet. If I fully flesh out sine, then cosine will be easier. So remember, sine, the inverse sine has a domain. Get out of there. Why am I not able to write? I'm never able to write, so what am I concerned about? The domain is -1 to 1, and the range is -π/2 to π/2. So tell me this. What's the sine of 150 degrees?
Pi, 1/2.
Yeah, because it's got a reference angle of 30, right? So the sine of 30 degrees, 1/2. Let me stop for a minute. You guys, does everybody agree with me? You guys okay out there? All right. So if I take the inverse sine of 1/2, am I going to get 150 degrees? We'll try it. What do you get when you do the inverse sine of 1/2? What do you get?
$30.
Yeah, you get 30 degrees, which makes sense because what is the range in degrees? What's the range of the inverse sine? Degrees. Say again, sorry.
90.
90.
90.
It can only give you outputs from -90 to 90. All right, so here's a huge note. You guys notice how slowly I'm talking. Inverse sine output is a reference angle. Depending on the problem, you could be in a different quadrant. The answer to the inverse sine will be a reference angle. Do you see how that 30 degrees is the reference angle to the right answer? So if I said I'm in the second quadrant and sine theta is 1/2, and you tell me the answer is 30 degrees, you have to be wrong because I'm in the second quadrant. But that's what your calculator is going to tell you, ain't it? But of course, why? What did we have to do to even let inverse sine frickin' exist? We had to restrict the values it was allowed to use. Poor little dude. So it's not going to be able to give me every possible angle. It's going to give me the best it can. It's going to give me a reference angle. Okay, maybe. All right, so okay. So you just got to realize, depending on the problem, you have to know what quadrant you're in, and you might have to adjust the answer you get from inverse sine, because it can only give you between -90 and 90, negative pi over 2 and pi over 2. What about cosine? Let's develop what inverse cosine is. So here's cosine. I love cosine. It's that octopus looking dude. So what's up with cosine? Am I going to be able to cut it the same way I did sine? Oh, you can do it, Jeff. Where am I at? Oh. My scale is really bad, but I don't care. Am I going to be able to cut it the same way I did sine? What is it? Why am I cutting it? What am I trying to make happen? Remind me. Why am I going to cut the domain? I cut you, domain.
Make it 1-to-1.
Make it 1-to-1. So I can't do it from here to here. So what's the next best place to do it?
0.
Good. Yeah, 0 to pi. Because that's where it has a problem. If I go past 0, it's got a problem. So let me chop it at 0. And then where does it have a problem? It's great. It's fantastic. It hasn't gone. It's having a great time. It's, oh shit. So let me cut it at pi. So let's see. So I have to restrict this domain to 0 to pi. So the inverse cosine, the domain will be -1-to-1 the same way as sine, but the range is going to be 0 to pi. All right, so like, for example, somebody help me out. What's the cosine of, what are you going to do, Jeff? 240 degrees. What's the cosine of 240?
1/2.
Yes, because the reference angle is 60. It's far away from the x-axis. Cosine likes x, it hates y. So it's going to be a little tiny. Now be careful. Not 1/2.
negative.
-1/2, Ellie. All right, now, can you please, in your calculator, do the inverse cosine of -1/2? What do you get? I'll do it with you.
120.
Oh, I'm in radians. Yeah, so you should get 120 degrees. Is that the right answer for what I've drawn? Is 120 have a -1/2? Yes. But what do I want? I want to be in the third quadrant. So not 120, it's got to be this way. So cosine kind of sucks a bit. It's not really reference angles. I really need you to see that. But it's still going to be, all right, if it's 120, that's where cosine's negative. So if I'm supposed to be in the third quadrant, it's going to be equidistant away on the other side. So 120 is 60 away this way. So the answer is 60 away that way, 240. Again, this is a trade-off. We had to chop it, so it can't give me all the angles. It can only give me between 0 and pi. We had to do that, or else this guy couldn't even exist. At the same time, it sucks really bad that I can't just plug it in that gives me the right answer. I have to stop and think, what quadrant am I supposed to be in? Holy shit. All right.
So you can only know the degree if you know which quadrant
Yes.
in.
Yes, technically. Now, if I were dealing, the nice thing is, I want you to realize, if I was dealing with a triangle, what's the largest angle a triangle could have? Yeah, just under 180, right? You with me? So therefore, inverse cosine loves triangles because it gives you the whole range of possible angles that could exist in a triangle. Are you guys understanding? What we'll see later, when we get to the law of cosines, the law of cosines is going to be the nice one. It's going to have no weird shit. It's going to always tell me the exact answer. The law of sines is going to be weird. It's going to have a couple places where it's like, oh, there's several triangles possible. Like, oh, damn, screw you, law of sines. But it's because this guy's outputs are all the possible angles that live in a triangle. What's the inverse sine's outputs? -90 to 90? What the shit, inverse sine? Drunk, buddy. Go home. All right. Anyway, sorry. It's a little preview of what's coming. Okay. All right. Let me see. Oh, let's do this and then we'll call it a night, I think. Let's talk about inverse tangent. Oh, you know what we haven't even done yet? Oh my goodness, Jeff. All right, let's talk, before we talk about, all right, let's just talk about freaking tangent. We haven't even graphed this thing yet. So this would be the last thing we do tonight. We'll graph tangent, talk about graph of cotangent. And then I think next time we'll talk about the inverses of both. Okay. I just completely forgot to do tangent and cotangent. So to graph this bad boy, let's do this. Can somebody tell me what angles tangent freaks out at? What is tangent defined to be? What's it defined to be in terms of other trig functions?
Sine x over sine.
So somebody else tell me, where will tangent freak out? Where will it be undefined? Anywhere that what is what?
Cosine equals 0.
Good, cosine equals 0. So Kurt, your answer is correct, but it was too specific. 90 degrees is one place that cosine is 0, but everywhere cosine is 0, tangent's going to freak out. You can do it, Jeff. There you go, buddy. You set up your scale. There you go, my friend. Okay. So everywhere cosine is 0, this thing is going to have what? I almost drew it. Wherever cosine is 0, the graph of tangent has to have a what?
Asymptote.
Asymptote. You guys with me? We're just going to kind of speed this guy through. We can get the main points that I want for tangent. Oh, and I might as well, so this is 0. Let me go one more up here. So, I mean, I'm not going to worry about that because I'm out of room. But it would be here also, right? So whatever this picture is, it's going to repeat in here. It's going to repeat back here. So what does it seem the period of tangent is? How long is this? How long is this? How long? How wide is how wide?
2.
Say it again, sorry.
2.
No, it goes from negative pi over 2 to pi over 2.
90
Uh,
degrees.
Pi.
I love you guys so much. Wait, what'd you say?
Pi.
Pi, yes. Yes. How far is it from negative 2 to 2? How far apart are those? How far apart are those?
It's 2 pi, right?
4.
They're 4 apart, right? How do you tell how far apart two numbers are? What operation do you use? What operation tells you how far apart two things are? Subtraction. Pi over 2 minus negative pi over 2 is pi. All right, so that's the period of tangent. Okay. Whew. So what is tangent of 0? It's sine of 0 divided by cosine 0. What's sine of 0? What's sine of 0?
0.
0. So 0 divided by not 0 is 0. Let's put pi over 4 in here. Pi over 4 is one you have to know for tangent. What's so beautiful about pi over 4? Because it's sine over cosine. What's true about sine and cosine at pi over 4? They are what? At pi over 4, sine and cosine are how related? At 45 degrees. The y piece and the x piece will be the same. Okay, thank you. I looked over at chat. All right. Sorry. So at pi over 4, since sine is equal to cosine, tangent is 1. At negative pi over 4, sine is negative and cosine's positive, so it's negative 1. So the tangent looks cubish. The tangent kind of looks cubish. See how it looks cubish? Especially when we make that point big. There we go. It looks cubish. Do you guys agree with me? It looks like a x to the third power, but it is not an x to the third power because it's not an x to the third power. A polynomial is not supposed to be bounded like this, right? So then it just repeats, just like any trig function. It's going to repeat that shape. It's going to repeat that shape. Oh, crappity doo dah. Let's just do it like that, right? So repeat, repeat, repeat. Same thing like every other freaking trig function. So this is really, really in your face. That's what tangent looks like. So what would I do if I wanted to get inverse tangent? How would I restrict the domain? Should be really obvious.
Where the sine's 0?
Sorry?
Where the sine's 0?
No.
Hmm.
Where's like the main graph that I made a repeat of? Where does the main graph live that I just made repeats of? Between what and what does the main graph live?
Negative pi over 2 and pi over 2.
Beautiful. So that's how I would restrict the domain. I would kill this and I would kill that. And now is that past the horizontal line test? Check. I like it. All right, so therefore, now can somebody tell me what is the restricted domain of Jeff? Hello, restricted domain of this trig function. I'll just do it. Negative pi over 2 to pi over 2, right? That's the restricted domain. In fact, I just made a mistake. That's an asymptote there, right? So it should be this. Because that's an asymptote, I can't include that place. What's the range? Yeah, negative infinity to infinity. So for the inverse tangent, the domain will be all real numbers, and the range will be negative pi over 2 to pi over 2. Notice how it's got the same range as sine does, inverse sine. You with me? Because tangent is primarily dependent on sine. Tangent is sine divided by somebody else. So tangent going like sine is a really good little memorization tool to use. It helps. Where sine is small, tangent's small. Where sine is big, tangent's big. Because they kind of go like each other. Look, they have the same range. Aw, that's so cute. So if I do flip this, it's gonna look like this. It's kind of neat. So that's just this thing flipped. Okay. I think that's enough. So next time we'll do cotangent will be very similar to this, but it's obviously not going to be exactly the same. Let me see. Yeah, that's a good place. Oh boy. So that's good. I was tired at the beginning of class. All right, guys. So that's enough for tonight. We basically finished chapter 8. We just have to talk about cotangent and inverse cotangent, but we're basically done with it. If you haven't done the quiz yet, you have until tomorrow morning. Let's see. I forgot to check if anybody had the balls to actually work on the quiz during class. It looks like no. Good job, guys. Okay. All right, guys. So let me know if you have to hang out afterwards. Otherwise, you can go away, and I'll see y'all tomorrow.
Thank you.
Sure. Let's see now. Amanda, are you okay? Carolina? You guys okay? Amanda, Carolina, Mason, Julius? Are you guys okay? All right. Hold on, let me do